Hello, this is Mr. White, and this video is on differentiating exponential functions with the natural base, base e. And here are our three exercises. So, e to the x is this wondrous function that is its own derivative. If we derive e to the x, we get e to the x. However, if the exponent is something other than x, of course, the chain rule does apply. So derivative of e to the u is e to the u, but times the derivative of u. So when we derive y up here, y prime will still be e to the negative x squared, but times the derivative of negative x squared, which is going to be negative 2x. So final answer, y prime equals negative 2x, e to the negative x squared, just rewriting it in the more standard way there. And in exchange for this being so wonderfully quick, that this may be the quickest exercise I've ever done in one of these videos, we should definitely check this by calculator. So type in the original y into y1 and then the derivative in y2. Here are some window settings that I found to be pretty good for this exercise. The negative 4.7, positive 4.7, that's based on the zoom decimal, although I did tweak the y min and y max. So here's what the graph looks like. And this is a great example of a type of graph where we can see the connection between the y and the y prime. It's worth taking a moment just to reaffirm in our brains here and notice that wherever this y graph is increasing, that's exactly where the y prime graph is above the x-axis, consistent with our understanding. Wherever y is decreasing, that is where y prime is beneath the x-axis. We notice that, of course, at the extreme, where we see a horizontal tangent line, that's where the derivative has a value of 0. We notice that as we go to at the end behavior, as we go way to the left and way to the right, the graph is certainly leveling out, approaching a slope of 0, and we see that the y value, or the output of the y prime graph, is also approaching 0. So let's finish by at least doing a little bit of a numerical verification here. Let's go to second calc number 6, dy over dx. Just pick some point at random. I've got 1 in there. That works. The derivative when x equals 1 is negative 0.7357. I jump down to the y prime graph and I see that same value. So this seems like a good confirmation. All right, let's go on to the next one. Okay, pretty clear. We're going to need the product rule here, so let's get right into that. Y prime is going to be the second function, e to the negative x, times the derivative of the first, 2x, plus the first function, x squared, times the derivative of the second. Again, we'll need the chain rule there. So e to the negative x times the derivative of its exponent, negative 1. And because the derivative of e to the x is itself, every time you end up using product rule or quotient rule or such on these functions involving e raised to some power, you're almost always going to get, practically always going to get some common factor there. So just be in the habit of factoring out the exponential. And when you factor that out, we get 2x inside the big parentheses. And then due to this negative 1, we'll get a minus x squared. And we also notice that there's also more that we can factor out from this expression. Let's bring in x out as well. And I'm going to put that in front of the e to the negative x. Now leave us with 2 minus x inside the parentheses. And that is about as much as we're going to be able to do with that derivative. And we spot right away that when written in this form, you can just very easily see what the critical numbers are going to be. We weren't asked to do this, but it's good to think it out anyway. We notice that one critical number is going to be at x equals 0. This one's going to give us x equals 2. And let's recall that as far as this one goes, the exponential graphs don't have x-intercepts. So e to the x looks like this, whereas e to the negative x looks like this. Either way, it doesn't have an x-intercept. There is going to be no zero, no critical number that results from this expression. And once again, comparing the graphs of the original to the derivative. Well, first of all, we do see that there appear to be extrema at x equals 0 and x equals 2. So that's a good sign. And again, the parts of the original y graph that were decreasing right here and right here, that's where the y prime graph is below the x-axis. The interval from 0 to 2, it appears, where y is increasing, that's where y prime is above the x-axis. And again, just to be absolutely sure, go to second calc, number 6, and let's pick, how about 3? And at that somewhat randomly chosen number of 3, we have a derivative of negative 0.149. Jump down to the derivative graph, and I see that same value, negative 0.149, so looks good. All right, let's go on to the last one. For this exercise, we see our natural log that suggests u prime over u. We see that when we take the u prime, we see a quotient in there, and that would suggest the quotient rule. But do you see something that we should maybe do before we even jump into the calculus, jump into the deriving? How about we take advantage of our log properties? So before we get to y prime, let's just rewrite y itself using the logarithmic quotient property. Let's put ln of the numerator, 1 plus e to the x, minus ln of the denominator, 1 minus e to the x. Now it's time to take our y prime. So now we'll use the u prime over u. This is our u, and we'll put that on the bottom, 1 plus e to the x. And the derivative of 1 plus e to the x, well, the derivative of 1 will give us 0. The derivative of e to the x gives us e to the x. And for the next term, we'll do the same thing, but using this as u, 1 minus e to the x. So we'll put that on the bottom, 1 minus e to the x. And the derivative of 1 minus e to the x will be 0 minus e to the x. Since this is a derivative and we're often interested in critical numbers, let's combine these into a single term with common denominators. And when we distribute out the numerators, we'll get e to the x times 1 minus e to the x times e to the x. We're just going to add the exponents here. So x plus x will give us 2x. Okay, minus negative e to the x times 1, which is plus e to the x. And finally, minus negative e to the x times e to the x, which again will give us plus e to the 2x. And that's all over our common denominator, 1 plus e to the x, 1 minus e to the x. We'll cross out the minus e to the 2x and the plus e to the 2x up top. We'll combine the e to the x's. We'll get 2e to the x. And although as a general practice, I typically like to leave things factored in our denominators or in our derivatives, in this case, it's kind of irresistible to go ahead and FOIL out that difference of squares pattern. So nothing wrong if you leave it factored, but if we FOIL that out, we'll get 1 minus e to the x plus e to the x, and then finally minus e to the 2x. So I'm going to call that done. So of course we could check in the same manner that we have been checking with the calculator, and I'll let you just trust me that it does check out. But I'd like to point out another interesting observation when graphing these on the calculator. Notice that the original y itself has a domain of only negative real numbers, negative values for x. And that makes sense because when we look at the equation for our original function, if x were equal to 0, that would make this e to the 0 power equal to 1. And then we'd have 1 minus 1 in the denominator, and we understand why that would be undefined. If x were positive, then this number is going to be greater than 1, which means that our denominator there, 1 minus a number that's greater than 1, that means that our entire denominator would be negative, whereas this numerator would be positive. We'd be trying to take the natural log of a negative number. And so we come to understand why the domain can't include positive values of x. So it is interesting to note then that the derivative graph, which does extend over here, kind of runs alongside the original graph, roughly. But it's interesting to note that the derivative graph has a domain that does extend into the positive x values. And that should remind you of a previous discussion where we went over why, when you integrate something like this, why you need to put the absolute value bars in the ln function for the antiderivative. If those absolute value bars had been there in the original function, we would get a graph that looks more like this. And that looks a little more complete there, where the domain includes negative numbers and positive numbers, the domain of the original graph. All right, so as easy as it is to just get caught in the grind of doing assignments, I encourage you to always be on the lookout for those kinds of insights. One final comment on this exercise. I mentioned earlier that the log properties were going to help us out and help make our differentiation a little bit easier. But I want to show you what it would look like if we had done this exercise without taking advantage of the log properties. So we would have started by doing the u prime over u pattern, and within that u prime we would have had to use the quotient rule, and we would have had fractions within fractions, so we would have simplified that out, had some like terms, had some terms cancel out, and in the end, of course, we get the same answer. And I'll say this is not the worst natural log derivative I've ever seen, but I do think it's another case where we see that the log properties help make our job a little simpler.